Okay, so we're going to look at some additional stuff to do with regression analysis. So first off, we're going to look at how we calculate R, and then we'll go on to talking about the coefficient of determination. So here's the actual equation for calculating R. You look at it and go, oh my God, do I have to know that? No, you don't. But that's the actual equation that is used to calculate R, and basically the calculator does it for you. Here's some limitations for when we use R. As it says here, we're going to be using CAS to get your calculator to do it. All right. So since R measures, here's some limitations. Since R measures the strength of a linear relationship, it would be inappropriate to calculate the R for data which is not linear. Which is why when we do transformation, where we check for residuals, that's part of that's to say, is what anything valid? Because if it's not linear, then we can't use that data. Outliers can bias the value of R. Consequently, if a set of data contains an outlier, then R is not a reliable measure of the strength of that linear relationship. So if there's an outlier, it's going to be hard to use that data. As it says here, it's good practice to draw a scatter plot for a set of data, and that's to check for the linear form and the absence of outliers. And also, having a scatter plot in front of you is useful because it enables you to estimate what the value of R might be so that you can actually check your calculations correct. So if it's looking something like, where's one? We've got some numbers here. Yeah, there we are. If it's looking like, say, this one, for example, and your calculator is telling you 0.5 and it's closer to like a 0.9 type thing, you know there's been some sort of mistake somewhere. Okay. Now, in terms of instructions, this is how you can calculate the your R and your R squared values if you haven't plotted the data up. This is one way to do it. I would suggest you actually plot the data because it does this stuff does it for you, but you can actually follow this process to actually generate the R squared, the A, the B, the R squared, and the R values. Okay, this will do it for you. This is a way I would be using this way if you're at a point where you don't want to plot the graph up first. Use method 1. Now, if you want to, it wasn't that one. It was this one here. This is the way you could also do it if you've plotted. So you've already got your plot. You've done your plot, and you've got your linear regression line, which is giving you this information here. And what's important to note here, as always, is that this is what the calculator's told you. This is calculator. This is how you need to represent it. How you need to represent your equation, especially when it's asking for in terms of variables. Okay. But more important for what I've been just talking about for R and what will come up as R squared is that if you follow these instructions after you've done your graph, you will get this information here. Okay. So that's actually doing the calculation part of R and R squared. Okay. And we know what R gives you the strength. Then we'll go on to the coefficient of determination. And what that's telling us, and basically the coefficient determination is just your R value and you square it. So it's the degree to which one variable can be predicted from another linearly related variable, and that's what we use the R squared for. Okay. That's how we calculate it. We multiply it by 100 to get in terms of percent. And there's a statement we use to actually, once you've worked it out, we can use a particular statement of what it's talking about. All right. So using the example from here, what does it mean? If we take a group of people, we find heights and weights vary. So, you can sort of say the coefficient of determination tells us that 64% of variation in people's height can be explained in this way. But there's a specific way we want you to write this. So you could be writing it like here. This is from a previous example. We're given the R, so we're given the R squared. We've said that this is your RV, this is your EV, okay, your exponential variable there. And so it's therefore 97% because we've done the R squared of the variation in CO level. This is your, your Y variable, if you want to think of it like that. So you know where to place it. Can be explained by the variation in traffic volume, which is your X variable. Okay, and the same sort of goes for this sort of stuff. You have a particular statement you use. Again, this is another example where we did we did this, where math was responsible. The math ability was the response variable, and so you've done that first. Can be explained by the variation in verbal ability, which is the exponential. Oh, sorry, exponential. Yes, it's the exponential variable. Okay. This is basically least squares regression line, which we sort of haven't quite shown you just yet in terms of the video, at least. We haven't shown you. This is the equation, the sort of equation you'll use. You can use if you're given this sort of information. Here's what you use in calculating B. Then you calculate A, and that can give you your regression line. You do need you need these 5 bits of information though to be able to use this sort of setup. And this is usually seen in an exam style question. Here's the calculating instructions I mentioned before is about doing a linear regression line and then generating your stats from that. And here was just an example that we did in class. So you can sort of see that idea of what you're doing. Okay. It's worthwhile going through a quick look through the linear regression analysis. So what we want to do, we want to construct a scatter plot to investigate the nature of the relationship between the variables, which is what we know how to do. We calculate the correlation coefficient to give a measure of the strength. We determine the equation of the regression line. Again, that we're using the calculator for that. So this one's calculator. This is done on the calculator. I'm just going to get a little bit of, interpret the coefficients of A and B of the least squares. Remember, this should be written in slightly different. It's Y equals A plus BX, where A is the Y-intercept, and B is the slope. So the gradient slope / gradient. You have to read the question specifically to say which one do you actually talk about. We can use the regression line to make predictions. Okay. And remember what I've talked about, interpolation, extrapolation. When is it, when is a good idea to use either one? Good idea to always use interpolation. It's extrapolation which can have an issue if you're not careful. We're using the coefficient of determination, remember R squared, to give a measure of the predictive power. We have a statement we can use for that. Okay, to use for this. Oops. Okay. We use a residual plot, which I haven't talked about here in this video, but that's something we can sort of go through in a different video. Remembering basically, if you've got a scattered pattern like this, it's random, and we say that it's linear. Both of these have a pattern, so therefore we say it's nonlinear. Okay. but we can do that in a separate video. What the slope. So in your you can write a report on your what you've seen, what your findings. But often what you'll find is the question. There'll be specific questions after specific things here. So we've got the slope. So which is previously known as m, but that's basically in our case that's b. So this would be b. The slope provides information about the rate at which the data are increasing or decreasing, and the y-intercept indicates the appropriate value for the data when x equals 0. Now remember, the y-intercept is got to be, you've got to look at in the context of the question, and sometimes the y-intercept has no relevance for that particular information because it might be talking about something that's not realistic, but you've got to look at the context of the question because it sometimes is relevant and sometimes it's not. It depends on that context. So here's an example where they've talked about experiment conducted by a drug company to test the effect of a new drug. The red blood cell count was recorded over a number of days, and we found this relationship. Okay, so remember, this bit here is your slope. So what it's saying is it's a positive relationship because there's no negative in front. It indicates that the number of the red blood cells increased by 17 per day. That's what the slope is telling us. And what the y-intercept is saying is that the red blood cell count was 160 at the beginning of the experiment. Okay, and that's, you have to have some sort of analysis that talks about that sort of information. Sometimes a bit more, your answer might be a little bit more detailed than that, but that's a general idea of what you're doing with a slope and intercept. Okay, here's just a nice little summary of what I've just been talking about. But remember, the slope can be positive and negative. If it's positive, then y increases as x increases. And if it's negative, y decreases as x increases. Okay, did I do an example here? No, I didn't. No. Okay, so that's sort of what you need to start doing for this one. I'm just checking if I've got more of an example here. No, I don't. That's already written. And this video is going to be too long now, so I'm going to sort of stop there. But that's the process you need to follow as you go through these sorts of questions for R squared. Okay, thank you.